Okay, this video here, 6.1, it's kind of a long section, so we'll probably split it into maybe 2 or 3 parts so that you can take a little break in between if you need to, or pause or whatever, but covers quite a bit of stuff, and some of it's new towards the end with our calculator. So you may need to watch a couple of times to make sure you're comfortable with that part, okay? All right, so 6.1 is going to deal with something that we call matrices, okay? A matrix is a rectangular array of numbers. Sometimes I think about it like a spreadsheet on Excel. You know, you can have several different rows and columns of numbers, and they can mean different things. So that's kind of what a matrix is, a little bit, if you think about it that way. Just a rectangular array of matrix. A rectangular array of numbers is what a matrix is. Notice that there are rows and there are columns. Rows are horizontal. So this matrix right here has 2 rows. 2, 4, 6 is row 1. 1, negative 1, 9 is row 2. It has 3 columns. Columns are vertical. Think about a house that has big columns out in front. Those columns are vertical. So column 1 is the 2, 1. Column 2 is the 4, negative 1. And column 3 is the 6, 9. The size of a matrix is called the order, or the dimensions of the matrix. It is the number of rows. So in this case there's 2 rows and 3 columns. So we would say it is a 2 by 3 matrix. Okay. The individual numbers that are in the matrix are called the entries or the elements. So the 2, the 4, the 1, etc. Those are either entries or elements. Okay. Notice this matrix is a 2 by 3. You can have really big matrices, okay? And you can, some people like to put these little subscripts in them so that you can indicate which element you're talking about. So for example, this A sub 23 is talking about whatever item is in row 2, column 3. So sometimes instead of saying, oh, just find the 7 in the matrix, they might say, oh, look at the number in location 2, 3 for the 2nd row, 3rd column. So sometimes people can say it that way. When you're naming matrices, you know, this one is a, let's see, you know, well, the n by n matrix because we don't know exactly how far out they're going. But this one up here, when we said it was a 2 by 3, it's the rows first and the columns second. So sometimes I think RC cola. When I'm thinking about the numbers in the matrix, the first number is the number of rows, the second number is the number of columns. So RC helps me remember that, okay? You can have a square matrix. Square matrix happens when the number of rows is the same as the number of columns. So here we have M rows and N columns. M and N are the same in this one. Both 2 rows, 2 columns are both 2's. So this is a square matrix. Here there's 3 rows and 3 columns, so this is a 3 by 3 matrix. It's a square matrix. The main diagonal is from top left to bottom right. So here the main diagonal has the 2 and the negative 1. On the 3 by 3 matrix, our main diagonal has 1, 2, and negative 1. Okay? That main diagonal is going to be kind of important coming up in a minute, so we just want to know what we mean when we say main diagonal. We're talking about from the top left to the bottom right. Matrices could also be just a single row or a single column, okay? So a row matrix, or sometimes people call it a row vector. This one right here only has 1 row. Notice it's got 4 columns, but it only had 1 row. Here's a column matrix because it had 1 column. It had 3 rows, but it was 1 column, so we call it a column matrix. Sometimes people call those vectors instead of matrices when it's just a single row or a single column because there are some physics applications that you can do with that. We're not going to worry about that much here, but just know that sometimes that's what they do in physics. Okay? All right, we name matrices with capital letters. So this matrix here, this 2 by 3 matrix is matrix A. This 3 by 3 matrix here is matrix B. If you would like to see how to put those in your calculator, I can show you how to do that. Let's say we had wanted to put in this matrix A right here. So over on the left-hand side of your calculator, the little inverse button, the X to the negative 1, is actually called the inverse button. Up above it says matrix. So if you want to get to matrix, you would hit the blue 2nd key and then the matrix button. And it's going to say, okay, naming, some math to do with matrices, or edit. And of course, if you're putting numbers into a matrix, you're going to have to edit first. So I'm going to arrow over to the edit menu and then pick whichever variable you're wanting to use. If you wanted to use matrix A, then you could pick 1. If you wanted to use matrix B, you could pick the B. So whichever one you want to pick. I've chosen A. It's telling me I'm working with matrix A. And the first thing it needs to know is the dimensions. Okay, and this is a 2 by 3, so I can leave my 2 by 3. If it was a 3 by 5 matrix, then I could put 3 and arrow, 3 arrow over and then put my 5 and hit enter, and it would create enough spaces for me to put a 3 by 5. Since this is a 2 row by 3 column, I'm going to arrow back up there and I'm going to say, oh, it's 2 by 3, and it will adjust the boxes accordingly so I can put those numbers in. Okay, I've already got these numbers in here, but I'll tell you what, let's change it. We'll put what's in B there. So B was a 3 row by 3 column matrix, and so now I can fill those in, and it's going to let me type in each square. So I had a 1 in the top left, a -2 in the middle at the top row there, and then a 3, and notice how it's changing these numbers to match what I had. Okay. Make sure after you hit your last number you press enter so that it fills that in. Okay. We will need to put matrices in our calculators a little bit later, so that's how you do it. Once you've got it in there like you want it, you can hit second and then quit, and it will take you back to your home screen, and it remembers what you put in for matrix A or B or wherever you put it. Okay. All right, one of the applications that we can use matrices for is to solve systems of equations. And I know that you solved systems of equations in previous math courses, in Algebra 1 and Algebra 2. So let's just briefly recap solving systems of equations to refresh your memory of what that was like and kind of what the answer or solution represents, and then we'll connect it back to matrices, okay? Most of the systems of equations that you solved were 2 variables. So you had 2 equations with 2 variables, okay, an x and a y. You can solve systems of equations that have more variables. So notice if you had 3 variables, x, y, and z, you would need 3 equations. If you had 4 equations, if you had 4 variables, a, b, c, and d, let's say, then you would need 4 equations. So however many variables you have is how many equations that you would need. Primarily in high school algebra, they focus on 2 variable equations that had 2 variables, so 2 equations. You may have done a little bit with 3 variables. But you probably didn't go beyond 3. In our course, we're gonna always assume that they are linear. We never have any x squareds or parabolas or circles or anything like that. Although in real life that could happen, that you had a system of equations where maybe you had some parabolas or circles. But for our purposes, we're always going to be dealing with lines if there's 2 variables, or you could envision maybe a 3rd dimension, with a 3 variable. Okay, the 3 ways, by the way, the solution to a system of equation is the ordered pair that makes all the equations true. Okay, so we typically think of it as 2 lines. These are both lines, and wherever these lines would intersect, that ordered pair where those 2 lines cross, that's the solution, because that's the combination of x and y that works in both equations. If you had 3 variables, you'd have to picture it in 3 dimensions, but you'd have an x and a y in 2 dimensions, and then the 3rd dimension will be going through the paper here for z, and that ordered triple would be the combination of 3 numbers that worked in all 3 equations. Okay, 2 variables, so 2 dimensions, is not that big of a pain to use. You solved those in previous classes. You use graphing, you use substitution, and you used elimination. Those are the 3 methods that you probably learned in previous math classes. We're going to use matrices as a 4th option, and it's particularly helpful if you start getting 3 or 4 variables because it gets really tedious. And actually, we can't even graph on a piece of paper if we had 3 variables, so it's nice to have some other options. Okay. Remember the graphing method, you got both equations in, say, graphing here. If you rewrote both of the equations in y equals mx plus b form, that first equation would be, if we brought the 2x over and divided both sides by 4, we would have y equals -1/2 x plus 1/2. 3 halves there would be 1/2. And the other equation, x minus y equals 9. If you solved and got y by itself, you brought the x over, divided by -1, you would get y equals x minus 9. So if you graph those two lines and look to see where they cross, you could practice that if you needed to. Lo and behold, I've typed in both of those equations, and when I hit my graph, there's the graph of the two of them, and I'm looking at where they cross. Sometimes it can be tricky to see on your calculator exactly where they cross, so you probably learned in previous classes that you could do second trace, find the intersection, and it would tell you where they cross at the point 7, 2. Okay, so we know that those two lines cross at the ordered pair 7, 2. Substitution and elimination, so let's do substitution. Substitution, you get one variable by itself in one of your two equations. So I think it would be easiest to isolate this x. So I could add y to both sides here, and I would get x equals y plus 9. And then I can substitute y plus 9 in the place of x in the other equation. So if I put y plus 9 in place of x in the other equation, I'd have 2 times y plus 9 plus 4y equals 6. We can solve that equation and we'll know what y is. So distribute the 2y plus 18 plus 4y is 6. Combine the y's. 6y plus 18 is 6. Minus the 18 on both sides. 6y is negative 12. And divide by 6. We get y is negative 2. Now that's the y. And that does match the, oops, where did I mess up? Oh, because I wrote it wrong over here in my graph here. They cross at 7, negative 2, don't they? And I just left my negative off. Sorry about that. So the lines crossed at 7, negative 2. Sorry about that. So when I solve using substitution, I got negative 2 for y. Now I need to know what the x is that goes with it. So I can take either of those original equations. It looks to me like the x minus y equals 9 is probably the easiest. And if y is negative 2, I can substitute that in. X minus negative 2 equals 9. Well, that's minus and negative. That's really plus. So x plus 2 is 9, minus 2 on both sides, and x is 7. So just like we did with graphing method, we see that when x is 7 and y is negative 2, that's the ordered pair that works in both of these equations. If I put 7 for x and 2 for y in both of these equations, it would work for both. Okay? So that's why the lines cross at the ordered pair 7, negative 2. Elimination, the third method that's up here, take those same equations, 2x plus 4y is 6, x minus y equals 9. In the elimination method, you want to write your equations so that all the appropriate variables are lined up. So my x's are lined up, my y's are lined up, my equal signs are lined up, and my 6's are lined up, or my constants, my 6 and 9 are lined up. Ideally, in substitution, when you add the two equations together, something would drop out, either the x's or the y's. In this case, that doesn't happen. 2x plus x is 3x. The x's didn't cancel. 4y plus negative y is 3y. The y's didn't cancel. So we can't just add them yet right here. But what we can do is maybe multiply this bottom equation maybe by negative 2. And when you do that, you distribute that negative 2, your top equation stays 2x plus 4y equals 6. But you multiply that bottom equation by negative 2, and you have negative 2x plus 2y equals negative 18 when you distribute. Now when you add them together, x's cancel, and you've got 6y equals negative 12. Okay? And then we keep solving. So we're going to divide both sides by 6. Y is negative 2. And if y is negative 2, we can put negative 2 back into one of our original equations for y and solve for x. So maybe 2x plus 4y, we now know that y is negative 2, equals 6. We can solve that equation. See, I rewrote the 2x plus 4y equals 6, but I put negative 2 for y. So 2x minus 8 is 6. Add 8 to both sides. 2x is 14. Divide both sides by 2, and x is 7. So just like with the other methods, we got that when x is 7 and y is negative 2, that's the ordered pair that works in both of the equations. So graphing method, substitution method, elimination method, we got 7, negative 2 for all three of those methods. So these two lines cross at the point 7, negative 2, and that's the combination of x and y that works in both equations. as much fun as that was, I don't particularly want to do that for this 3 by 3 system here where there's 3 variables. So let's see if there's some other ways that we can do it using matrices. Now, in previous math courses, it's possible that you already use matrices. I would guess that you probably use something like the determinant or inverses or something like that to solve systems of equations with matrices, and that's fine. There's nothing wrong with that, but we are going to learn a system called row operations, okay, or row ops. That's the program that we put in your calculator. Just a different way to use matrices. And as you move forward in mathematics to some other courses that you might take later, those row operations come into play, particularly if you ever take a course called linear algebra or something like that. So that's why I want to show you how to use the row ops program. It's not to replace determinants or inverses or any other way that you may have used matrices before. It's just to show you another way. Like I said, the row operations do come into play in some future math courses, so they want to make sure that you kind of see how that works. Okay? All right, so remember, a system can have more than 2 variables and more than 2 equations, and so those 3 methods that we just looked at, graphing, substitution, elimination, can get really complicated. So matrices gives us another option, okay? Let's see how these matrices can be used to write systems. Remember how when we did the elimination, how we lined up the x's, we lined up the y's, we lined up the equals, and we lined up our constants, our plain numbers at the end. We still need to do that if we're going to use matrices. So right here, notice that there's no x in this equation, so I'm going to put a 0x right here just to represent, so all my x's are lined up, my y's are lined up, my equals are lined up, and then my constants are lined up. So I'm in the order I need, and I'm just going to write the numbers down and not worry about the variables. So 3 and 0, because those are my x values. The constant, or the coefficient rather, in terms of in front of this negative, or in front of the negative y here is a -1. The coefficient in front of the y in the second equation is 5. We don't need to put anything for the equals, and then we'll put our constants at the end, so 10 and 12. Okay, this is the matrix that we can use. The official term for it is an augmented matrix. Augmented matrix is just a way of saying, hey, we took some equations and we wrote a matrix to represent it. That's all that's saying. Some people like to put a line right here where the equals would be. I typically put that. Your calculator will not. If you recall that matrix that we typed in here a while ago, it will not have the line where the equals was, but that's okay. I personally like to draw the long line. Visually, it breaks it up for me. I realized that my x's and y's were over on the left, and that it was my constants over here on the right. Okay, but you don't have to put that line. By the way, my calculator, the matrix I typed in a while ago, if I just want to call it up and look at it on my screen, I hit second matrix, and this time I don't want to edit it, I just want to look at it, so I can pick number 1 because that's where I put it, and then when I press enter it says, oh yeah, your matrix A, those are the numbers that you put in a while ago. So that's what it looks like in your calculator. Notice it does not have that long line where the equal sign would have been. On number 2, it's not ready to type in yet because it doesn't have the x's lined up, the y's lined up, the equals, and then the constants. So we're going to have to do a little manipulation to this equation here. So I would distribute my 3. I'd have 2x plus 3x plus 3y equals 1. Combine all the like terms, and we'd have, let's see, 2x and 3x is 5x plus 3y equals 1. So that's the format we want, x, y equals and a number. On the other side, other equation rather, I distribute my 6. 14 equals 6x minus 6y. We just have the equal sign, and the 14 is on the wrong side, so we could rewrite that as 6x minus 6y equals 14, and that's fine. And now we've got x, y equals number, and this one is x, y equals number, so we're good to go. So 5 for the x, 3 for the y, 1 for the constant at the end. And my other equation had a 6 for x, -6 for y, and a 14 for the constant at the end. So there's my augmented matrix. It does not matter which equation is the top line. So since I had the 5x plus 3y equals 1 as my top equation, I put the 5, 3, 1 on top. But if I had reversed it and put the 5, 3, 1 on the bottom, that would be okay. But you do have to have the 5, the 3, and the 1 together on one row of your matrix. Okay, you can't put the 5 and the -6 together. It has to be the same values from that equation. Okay? Notice on number 3 that there's an extra variable. This one has an x and a z. This equation has a y and an x. This equation has a z and a y. So there's 3 variables. So that means we need to have our x's lined up in one column, our y's lined up, our z's lined up, our equals, and then our plain numbers at the end. So we need to manipulate each equation to reflect that. Notice this top equation has an x and a z, but it's missing a y. So we could say x plus 0y plus z equals -1, and then we've got it written in the proper order. Second equation is missing the x. Oh, no, sorry, it does have an x, and it's on the correct side. It's just the 2x and the y are in reverse order. So I could put my 2x first, my y second. It's missing a z, so I'll put plus 0z, and then my constant at the end was 5. Last equation is missing an x, so 0x minus y plus z equals 3. So you may have to rearrange to make sure that you're in x, y, z order, and then your equals, and then your constants. Then when I put it in my matrix, my x column will be 1, 2, 0. My y column will be 0, 1. Hopefully you recognize that's a 1 in front of the y, and then a -1 in front of the last y. My z column will be 1, 0, 1. And then, I can put a long line for the equals if you want, and then you have your constants at the end. So -1, 5, and 3. And there's your augmented matrix. That long line is optional, but I found that it helps people. Okay, so now number 4 and 5, they've given us an augmented matrix, and they're asking us, hey, what were those equations that were originally there? If it's okay with you, I'm going to start with number 5 here. So the original equations that are represented here in this matrix, we take that top row, it's saying -8x plus 7y equals 113. And then our bottom equation would be 2x plus 0y. I don't really need to put the 0y, so I'm just going to put the equals 1/3. And so that's the system that we had right there. It would not be wrong if you put the 0y, but you don't need it. Okay? What's interesting about number 4 here is, if you'll notice, you see how there's only 1s on the main diagonal and there's 0s in these other places? So as we read across, it's saying 1x plus 0y plus 0z equals -3. Well, there's not really any need for us to write those zeros. Remember, we left it out over here. So we can leave those zeros out. So what's cool about this is when you have 1s on the main diagonal and 0s below and above that main diagonal, they're really just telling you exactly what x, y, and z are worth. So this right here is really just saying, oh, 1x, or x, equals -3. The middle row here, notice all there is a y. There's 0 x's and 0 z's, so it's only got the y. They're saying, hey, y equals 0.05. And then the bottom one, there's no x, there's no y, there's only a z, a single z, or 1z, equals 12. Okay, so what's cool about this is, and this is the whole idea behind using matrices, is probably this system of equations did not start out with these boring equations. It probably started out with maybe, 3x plus 4y minus 18z equals 72. And the second equation might have been 7x minus 3y plus 9z equals 5, or whatever they were, okay? So 2x, -2x, minus 41y plus 18z equals 7.4, or whatever the equations were. And what they did was they did a series of row operations. They performed items on entire rows until they had manipulated it to look like this. So for example, if I wanted that 3 to be a 1, which I do because I want a 1 in the top left corner, I can multiply this whole row by 1/3. 1/3 times 3x would give me just 1x. 1/3 times 4y would give me 4/3 y. 1/3 times -18z is -6z. 1/3 times -72 is, what is that, 24? Okay? Or whatever it is. And so now they would have a 1, 4/3, -6, 24 in that top row. And the second row would still be 7, -3, 9, 5. And the bottom row would still be -2, -41, 18, 7.4. And then they can say, okay, well, I want a 0 underneath that 1. So what could I do so that this 7 would become a 0? Well, if I multiply this 1 by -7 and add it on, then I could get a 0 in that spot. So those are called row operations, and that's the next part that we're going to look at in 6.1, because we're trying to manipulate the equations until they look exactly like this matrix right here, and we can read off exactly what the x, the y, and the z are worth. And we'll look at that in the next video.